This video will focus on colligative properties, which means we're going to be looking at how putting a solute into a solvent will affect the solvent's properties. And then we'll also look at the math behind boiling point elevation and freezing point depression. So when we're talking about colligative properties, what we're talking about is a property that's dependent on how much solute is put into solvent. Okay, we're actually looking at how the property of the solvent is affected by a solute being dissolved in it. It's independent necessarily of the identity of the solute. We'll look at how the identity affects it slightly, but it's really more about the solvent in this case than the solute. The solute does have to be a non-volatile solute though, and what that means is that it's not a solute that's generally trying to escape from the solvent actively. So basically we're talking about solid solutes. If we're talking about a gas solute, since those escape so easily, they don't affect your solvent the same way. So there are 4 colligative properties. When you put a solute into solvent, you find that the solvent's vapor pressure decreases, the solvent's boiling point goes up, the solvent's freezing point goes down, and then the solvent's osmotic pressure also changes. We're not going to focus on osmotic pressure at all, we're just going to focus on the first 3. But again, these are all properties that are affected by putting a solute into the solvent, and they're all the solvent's properties that are affected. So your vapor pressure. Your vapor pressure, if you remember, is the amount of vapor that is going up off the surface due to the Maxwell distribution, the fact that some particles are hot enough to escape the intermolecular forces and become a gas. What we find is as you add solute to solvent, the amount of particles that can escape decreases. We have less vapor pressure when we're dealing with a solution than we would have if we were dealing with a pure solvent. And the idea here is simply that when you have a solute present, it's getting in the way of this solvent's ability to vaporize. Okay? It becomes less volatile. It can't escape the surface the same. So if you look at the diagram on the right, you see the pure solvent on the left has a lot of blue particles coming off, where once it's a solution, you have less blue particles. So your vapor pressure, the pressure created due to evaporation, goes down when you're dealing with a solution. The next colligative property is boiling point. We find when your solute is present in your solvent, your boiling point is higher. And we can kind of explain this if we simply understand what boiling is again. To boil something, you need to overcome your force of attraction to escape into the gas phase. But when you dissolve something, essentially what you're doing is you're increasing interaction between particles, right? You need that hydration. You have your particles actually becoming intermeshed into the solvent. So basically your solute particles are totally in the way of you breaking up your intermolecular forces. So you can't boil at as low a temp as normal. You have to not only break the intermolecular force of attraction between the particles in the solvent, but you also have to break them between the solute, and that requires more energy. There's lots of practical cases where we use boiling point elevation. Sometimes when we make candy or we make maple syrup, what we're actually doing is adding a sugar to the water, and we're looking at what temperature it boils at, and that's the temperature that we're making the candy at. So if you're making like caramels or a hard candy, it's all about that boiling point of the new solution, which is different than the boiling point of the solvent. If you're boiling water to make spaghetti or make some kind of noodle, a lot of people add salt to the water. And the idea here is that you actually would boil at a higher temperature so that you would cook the pasta faster because your temperature is hotter. We also use this as coolant in our car, right? The coolant we use is designed to have a higher boiling point so it won't become a gas as it absorbs energy. Freezing point is on the opposite of boiling point. We actually have a lower freezing point than normal. And if we, again, understand what freezing is, for freezing to happen, intermolecular forces have to all come together and be increased. And if your solute is present, it basically gets in the way of our intermolecular force of attraction. So you have to be even colder than normal for them to find each other to become a solid. We use freezing point depression in times where we don't want a solid to happen. So antifreeze and salt on the roads, and even when they have different windshield wiper fluids in the winter, those all use freezing point depression. If you look at a phase change diagram based on colligative properties, what you see here is an expansion of that liquid phase. Okay, the purple pinky lines are for a normal solvent and the blue lines are for a solution. So since you have a decrease in freezing point and an increase in boiling point, you end up with a wider range at which you're at a liquid because you can't change phase quite as easily. Now these again are for non-volatile solutes, which is usually talking about a liquid with a solid solute being dissolved into it. So how do we mathematically calculate how much we have elevated or how much we have decreased our boiling point or our freezing point? Here's your equations. Okay, one for freezing point, one for boiling point. The change in temperature, okay, so the amount you have elevated and the amount you have depressed equals a constant that will be given to you times the molality, so the concentration of the solution, times by N. The deal with N is that when you add a solute to solvent, you potentially have dissociation. When you have dissociation, you actually increase your effective concentration because each particle is present and in the way in terms of being able to boil or being able to freeze. If you add a molecule, a polar molecule, to your solvent, like sugar, remember that falls apart, but it doesn't dissociate into ions, so that doesn't change your concentration. But if you put sodium chloride in there, NaCl, that will dissociate into Na and Cl. She'll actually have 2 moles of effective solute into your solvent. So you're going to multiply your concentration by 2. If you had potassium phosphate there, where it actually separate into 3 potassiums and 1 phosphate, you'd have an effective concentration with 4 solute particles being in the way. So you'd have to multiply your concentration by 4. So that's the one new thing that's a little tricky when it comes to these math problems, and I'll help you with that tomorrow in class. But N is your number of particles that your solute will dissociate into as it falls apart into your cation and anion. So if there's a subscript on them, you just have to make sure you add that into the number. Now you see there with the potassium phosphate example, I didn't dissociate the phosphate because that'll actually stay as PO4 minus 3. But potassium will dissociate into 3 potassiums, which will affect your final concentration. So you're taking your molality concentration and multiplying by the number of particles your solute will dissociate into to get your effective concentration. And then you times that by a constant to see how the boiling point or the freezing point changed. So here's 4 potential solutes for us to look at. The first one would dissociate into 2, so N would be 2. The second one, sodium sulfate, would separate into 3, so your N would be 3. The third one is a polar molecule, so that'll dissociate into 1, and then you have that potassium phosphate example again, which will go into 4. So here's an example problem we'll look like what's a boiling point when I have a 4.75 molal sugar solution when water is my solvent. So I'm dealing with the boiling point of water, and I'm dealing with boiling point elevation. So my change in boiling point will be calculated by taking a constant times my molality times the number of particles that solute will dissociate into. So for this problem, I give you the constant of 0.512 degrees Celsius per m. Once I multiply those, I'll have degrees Celsius left over, which is awesome. My molality as given in this problem is 4.71 m. And then my N, I have to figure out how much the sugar dissociates into. Because it's a polar molecule, it doesn't ionize, it's just 1. So now you just plug it in, 0.512 times 4.75 times 1. And that equals 2.43 degrees Celsius. Now this problem isn't done because I'm asking for what's the new boiling point. And what you calculate in a colligative property problem is what your change in boiling point is. So my change in boiling point is 2.43. Water normally boils at 100, and since this is boiling point elevation, it's going to be 100 plus this change. So I'm going to end up with a new boiling point based on dealing with a water solution of 102 degrees Celsius. That's my new elevated boiling point. So go ahead and try the form, and we'll work specifically on this concept and math in class tomorrow. Have a nice day.